These are the frequently asked questions for section 6-8, day 2 in Algebra 2. I'm going to start with the graph each function number 29. So for number 29, what we want to use here is y equals 2 cubed roots of x as our parent function. And as we talked about, what we want to use with this is just our standard perfect cubes. And we want to tuck them in there and we'll get, our normal results, except this time we have to multiply by 2. So when we put the negative 8 in there, we get a negative 2, but times 2 will give us negative 4. We put the negative 1 in, we get the negative 1, but times 2 will give us negative 2. And again, we're going to see that symmetry from this. So that's the shape of the graph. That's absolutely where I want to start. So negative 8, negative 4, and then negative 1, negative 2, 0, 0, 1, 2, and then 8, 4. There is the shape. Of my graph. And now just to kind of point them out to myself in a minute here, I'm going to go ahead and mark those 5 points that I started with a different color here. Just so that I have all my ducks in a row when I go to do my h and k values. So because we have x minus h and it's x minus 6, that means my h value is 6. So this is going to need to go 6 units to the right. And then my k value of negative 9, ooh, these are going to bring me pretty close off the grid here. If k is negative 9, I'm going to need to go down 9. So for those 5 points that I just graphed, that's what I need to do. I need to make sure that I move them 6 to the right and 9 down, and I'll just start at what was 0, 0 before. So 1, 2, 3, 4, 5, 6, and down 9. From there, I can move appropriately, given what I already know. And this one is, like I said, going to go off the grid a little bit here. But I know what the shape is supposed to look like, so there it is. For number 29. And I'm just checking here to make sure they didn't want to talk domain and range. It's kind of silly with cube root functions anyway because it's all reals, but just wanted to make sure there wasn't anything left in the problem that I needed to do. Let me go to the next page here. And number 35, it says rewrite each function to make it easy to graph using transformations of its parent function and describe the graph. So I look at the problem right away and realize this is a square root function. And obviously I'd like to have an a value out in front that I can see. Well, I notice there's a number in front of the x, and I don't want that there. So what I'm going to do is I'm going to factor that out. So what I just did was I just factored the square root of 25 out of the whole thing. And if you're saying, can you do that? Well, we know we can already do that because all we're doing is dividing when we're factoring. So we're dividing the square root of 25 out of a square root. So this would give you y equals 5, square root of x plus 5 minus 3. And then we would want to take a peek at this as far as how does that fit that pattern that we have. So we write that generic y equals a square roots of x minus h plus k. And then it says we want to describe the graph. All right, so if I had to graph this, I would graph y equals 5 square roots of x as the parent function. Then translate it. Then translate. Well, my h value is going to be negative 5. Since it's x minus and it became a plus, they must have put negative 5 in there. So then translate 5 units left, and our k value of -3, that's going to be 3 units down. And that's the description that I need to give right there. Oh, I realized I was going to do 33 for you as well. I'll back up and do that one. This one I think is probably a little more involved, but I'll go back and do 33 for you as well. Just remember, we want that x minus h piece to be by itself underneath that radical. All right, so what I'm going to do now is go back to 33 for a second. And again, you know, thinking, hey, this is a square root, but I need square root of x immediately. No coefficient in front of it other than 1. So what I have to do is I have to factor out a square root of 4. And then I know what the square root of 4 is. It's 2. And then in algebra, when things are sitting right next to each other, that is going to be multiplication. So there is my end product, and now all I have to do is describe how I would graph that. So I would graph the parent function, y equals a square roots of x, which in this case is y equals -4 square roots of x. Then translate. If our h is a +4, that was because it went in as a -4, because x minus a -4 gave them x plus 4. So translate 4 units left. And that is a description of the graph. 38 says we want to actually graph each function, talk about the domain and range. So in number 38, we have y equals 4 cube roots of x minus 2 plus 1. This is a really good problem. It has everything, you know, that we need here. So it'll be y equals 4 cube roots of x as the parent function. And because it's cubed root, we go with those standard perfect cubes. And we're going to end up multiplying by 4. I'm probably going to need to go by, well, at least 2's when I get done here, but we'll discuss that in a second. So if I put my -8 in there, I get -2, and -2 times 4 will give me -8. A -1 in there, -4, 0, 4, and 8. And I'm taking a look at my translations, and they are going to have me go 2 to the right and 1 up. You know what, I will be able to make it okay on this one then, because my 8 will leave me enough room for that. So 0, 0, -1, -4, -8, -8. The smart board to let me up there a little bit. There we go. All right, now let me be able to behave. And -8, -8, 1, 4, and 8, 8. Like so. And then y equals a cube roots of x minus h plus k will go 2 to the right and up 1. So each of those 5 points I just graphed, 2 to the right and up 1. Which gives me this graph right here. And then they did want us to find domain and range. But for these, that's always kind of silly because any cubed roots are going to be all real numbers. And that's going to be our domain and range. And let me make sure that that was all they wanted me to do. Graph each function, find the domain and range. All done. All right, number 39 is a square root function. And my parent function will be y equals 1/2 the square root of x. So I want to put in those perfect squares that we've been using. And when I'm done putting them into the formula, I have to multiply them by 1/2. So square root of 0 is 0, times 1/2 is 0. Square root of 1 is 1, 1 times 1/2 is 1/2. Square root of 4 is 2, 2 times 1/2 is 1. And then the square root of 9 is 3, and 3 times 1/2 is 1.5, or 3/2 or 1.5, whatever you need to get that graphed. And then while I have it set at the screen right now, I'm going to go ahead and write down that my h value is 1. So that's going to be 1 to the right. And then my k value is 3. So that means I'm going to be moving this 1 to the right and 3 up. So let me get the original on here. And then my translation. And it is graphing a little high here. 0, 0, 1, 1/2, 4, 1, and 9, 1.5. So there's the shape. And then, like I said, I just have to move this 1 to the right and 3 up. There it is. Paying attention to the fact that my new starting point there is going to be 1, 3. So with these, we use that little starting point to figure out our domain and range. And the domain is x is greater than or equal to 1, because this is going to the right forever. And then our range is y is greater than or equal to 3, because it's also going up forever. Then I believe there was another one on this page I was going to go through with you. Yeah. This says, suppose that a function pairs elements from set A with elements from set B. Recall that a function is called onto if every element in B is paired with at least one element in A. So this is assuming that you remember from exponential that we have what's called an onto function. If every element of B has some value in A that it came from. So you have this A, and it needs to spit out all of the B values that you have. A says the graph shows a transformation of y equals the square root of x, and write the function. And easy enough to just figure out where your new hk is at 2, -2. So that will give you y equals. And then if you want to figure out what A is, notice that this is that same movement that we just have with the square root of x. You know, there isn't any stretch or compression right there. This would be our 0, 0, and this would be our 1, 1. So that's just going to be our normal square root. To the right would be x minus 2, and then down would be minus 2. So y equals the square root of x minus 2 minus 2. Now, next part, B, says what are the domain and the range of the function? Well, this is just a matter of that starting point there. So x is greater than or equal to 2. And range would be y is greater than or equal to -2. And then it says for the domain, is the function onto the set of, here's what's important here, non-negative real numbers. Non-negative real numbers. And so the answer to that is no. And let me get this out of the way here. And I will just pick a point to show you why. Right here, let's look at 3, -1. If this is supposed to be onto the set of non-negative numbers, when we put the value of -1 in, we are supposed to be able to figure out a number that will give us something that's not negative. And as you look at this, if you put a 3 in, you're just going to get -1. That's it. So the number 3 is paired with -1, which is not a non-negative real number. So 3 is paired with -1, which is not a non-negative real number. And that's what we see there. And yeah, that's not the only one that you could pick, but it's kind of a nice grid point that you could pick for that one to explain it. Then number 43 says rewrite each function to make it easy to graph using transformations of its parent function and describe the graph. So this is again just a matter of saying, hey, I see that there's a 25 in both of those, and that would leave me with x minus 4 minus 1. So that's going to be 5 square roots of x minus 4 minus 1, and then describing what I would do. And I would need to graph the parent function. And that parent function would be y equals 5 square roots of x. Then translate. So we would translate 4 units right, because h is going to be a 4, and 1 unit down. So very similar to the ones that I did earlier. Then number 45, we would take the cubed root of, the cubed root of 2 out of there, huh? So cubed root of 2, no we wouldn't. Let's go ahead and take the 8 out. It doesn't make much sense to just pull the 2 out of there. That's not going to do any good. So we're going to pull the negative cubed root of 8 out of there. And again, you have to think of it as division. So if we pull that cubed root of 8 out, which will give us a 2, which is nice, we have to think, okay, 8x divided by 8, that would give you 1x. And then negative 2 divided by 8, that would be a negative 1/4. And that is definitely better than what we would have been saddled with if we'd have taken a 2 out of that. And it, it could be graphed with a graphing calculator, or we could have done it by hand, but better if we have that HK, and even if H is, 1/4, we can deal with that shift a little bit better. So that's what we would put down. And then I want to describe that graph and say graph a parent function y equals -2 cubed roots of x, then translate 1/4 unit right. No k value on that one, so we would just stop with that. And they're not having us graph these, they're just having us talk about those translations as we go through there. Just get them into that AH and K is what they're basically having us do. Then, number 53 was the next one I wanted to go through with you. It says the size of a computer monitor is given as the length of the screen's diagonal D in inches. The equation D equals 5/6 square roots of 3A models the length of a diagonal of a monitor screen with area A in square inches. A says graph the equation on your calculator. Well, we know what it's going to look like because this is a square root function. And that 5/6 in front tells us that it's going to be squished. So I'm just going to go ahead and make a quick sketch of what we know that's going to look like, because it definitely would start at 0, 0 there. And B says, suppose you want to buy a new monitor with a screen that's twice the area of your old screen, and your old screen has a diagonal of 15 inches. What will be the diagonal of your new screen? Well, the first thing that you would want to figure out is what's the current area of your screen. So I guess I'm old school, but I would go ahead and solve this for A. I would actually write that inverse operation by multiplying both sides by 6/5, then squaring both sides, and dividing by 3. And then it would just be a matter of grabbing your calculator and saying, okay, the diagonal I have right now is 15. So 15 squared is 225, and I'm going to need that times 12/25. And that comes out to 108. Now, we want to double that. So 2 times 108 is 216. And now we want to put that into the original formula so that we can find the diagonal. So the diagonal will equal 5, 6, square root of 3 times 216. So let's see here. I have my 216 in here. I'm going to take it times 3, take the square root of that little monster, and then multiply that times 5, 6. 21.21320,344. So the diagonal of your new screen approximately, well, let's go with 21.2. Let's see what the book rounded to since they didn't tell us which way to go with this. Yeah, they left it in tenths. So approximately 21.2 inches for that new diagonal. Although, you know, you probably can't get a TV that's exactly 21.2 inches, but you take whatever was close enough. All right, probably something higher if you wanted to make sure you doubled the area. Physics. You can model time, t in seconds, an object takes to reach the falling from a falling height h in meters by. T of h equals the square root of 2h over g. The value of g, 9.81 meters per second squared, which you probably used in science class before. If an object takes 7 seconds to fall to the ground, what was its initial height? And again, I'm going to go old school on this one. And go ahead and solve it for that h. And I'm just going to use t instead of t of h here for that variable of time, just so that nobody gets confused by the two h's in there. So first thing we would do is square both sides and get t squared equals 2h over g. Then we'd multiply both sides by g, and finally divide both sides by 2. And that will get us the height. They told us that the value of g was 9.81 meters per second squared, and that it took 7 seconds to fall to the ground. So we're going to have 9.81 times 49, and then we're going to divide that by 2. 240.345, what was the initial height? Again, that probably just rounding this to seconds, but let me double check here. Oh my goodness, they wrote the whole thing down. Wow. Okay, so we'll just put the whole thing down. H equals 240.345 as the initial height in meters. Well, that's probably why they left it. It's a bigger unit of measure, so think of a meter stick. That's why they're leaving the whole thing there. Then, that might be it. That is it from section 6.8, day 2.